September 1944. A Filipino guerrilla fighter crouches behind a bamboo wall in a village on Leyte, watching a Japanese pillbox about 40 meters away. The position has resisted 3 conventional assaults. 2 guerrilla fighters are dead. Grenades have failed to penetrate the firing aperture. The guerrilla carries 2 salvaged fuel canisters, connected by a rubber hose to a pipe nozzle fashioned from plumbing fittings. The whole assembly weighs around 12 kilograms, held together partly by wire binding, partly by friction. The fuel mixture is gasoline, with motor oil added at roughly a 4-to-1 ratio. The oil increases viscosity, helps the fuel cling to surfaces. A wick of kerosene-soaked cloth wraps the nozzle. The guerrilla lights the wick, opens both canister valves at the same time, and squeezes a lever that compresses the fuel line against the pipe body. Pressurized fuel meets the burning wick and ignites. A jet of burning fuel extends about 4 meters, striking the pillbox aperture directly. The burning mixture enters the position. Within 12 seconds, the occupants are no longer firing. The guerrilla closes the valves, withdraws behind the wall, moves to the next position. The homemade flamethrower cost nothing beyond salvaged materials and about 3 days of assembly. It worked because it only needed to work once. Irregular forces across occupied Asia and Europe faced a fixed fortification problem that was tactical and material. Japanese defensive doctrine emphasized small pillboxes, concrete or earthwork with narrow firing apertures. Designed to resist small arms fire, to deflect grenades, to provide covered fields of fire. Rifle fire could not destroy them. Grenades bounced away unless perfectly placed. Satchel charges required approaching under direct fire. Military flamethrowers, when available, were heavy, specialized, and inaccessible to guerrillas without supply lines. What irregular fighters needed was a way to project burning fuel into enclosed positions, built from materials already around them. The improvised flamethrower was the minimum solution. Construction principles appeared independently in multiple theaters. The engineering was simple. Flammable liquid under pressure, directed through a nozzle, ignited at the exit, becomes a stream of fire. Only 4 elements are required: a fuel container, a pressurization method, a delivery tube, and ignition source. The challenge was building it with what was available. Most common design: 2 fuel canisters, 5-liter or 10-liter jerrycans salvaged from equipment. 1 held the fuel mixture. 1 held compressed air or acted as a displacement pump. Rubber hose from vehicles or irrigation systems connected to a plumbing pipe nozzle. Pressurization varied. Some used bicycle pumps. Some used manual compression of a second canister. Some relied on gravity alone, elevating the fuel above the nozzle. Gravity designs had a shorter range. Pressurized designs extended range slightly further. Fuel mattered. Pure gasoline projected well, but risked ignition traveling back toward the nozzle. Adding motor oil or grease thickened the mixture. A ratio of roughly 75% gasoline, 25% oil, produced a burning stream that held together in the air. Burn temperature around 900 to 1100 degrees Celsius. Enough to ignite wood, fabric, vegetation. Enough to cause severe burns. Effective range: 3 to 5 meters for gravity-fed systems, 4 to 8 meters for pressurized ones. Far shorter than military equivalents, but adequate for projecting flame through apertures. Range was the critical limitation. Operators had to approach under covering fire, often firing while advancing, closing distance until the flame reached the target. Documented use occurred in the Philippines, Yugoslavia, French Indochina occupied Europe. Filipino guerrillas used improvised flamethrowers during Leyte, when military models were unavailable. Yugoslav partisans recorded a similar use against garrisons. French Maquis employed incendiary devices in sabotage operations. Parallel development across continents, same solution, same basic design. Comparison with military models shows the gap. The American M2 flamethrower carried 11 liters of napalm-thickened fuel at 200 pounds per square inch. Projected flame, 40 meters. 45 seconds of burn time. The improvised version, 8 liters, low pressure, 4 to 6 meters range, 20 seconds of usable flow. The range ratio is roughly 1 to 7. But in jungle terrain, where visibility might be 10 meters, that difference shrank. The danger to operators was substantial. Hose connections could fail, fittings could crack, ignition wicks could falter, over-pressurized canisters could rupture. Documented cases exist of fighters burned by their own devices. They understood this. They accepted it, because the pillbox could not be taken otherwise. Post-war analysis confirmed improvised flamethrowers appeared wherever a regular supply was absent and fixed positions blocked progress. Crude, dangerous, limited, but effective for one specific problem. The guerrilla fighter on Leyte survived the war, returned to civilian life. His name is not recorded in accessible archives. The pillbox he destroyed was one of hundreds reduced by irregular forces through improvised means. The device he built cost nothing, required no supply chain, solved a problem in 3 days of work. The position was destroyed, had resisted for 2 days, cost 2 lives, ended in 12 seconds. Military effectiveness is sometimes measured in resources invested versus objectives achieved. By that measure, a homemade flamethrower built from fuel cans and plumbing fittings did exactly what it needed to do.